Hey guys, welcome to the discussion in real analysis. In this series, we are discussing on topics of the book Principles of Mathematical Analysis by Walter Rudin. The target of this video is part B of Theorem 9.8. Already we have covered in our last video part A of Theorem 9.8, which we had discussed as a lemma for this result, part B. And the lemma means part A was actually concerned about that if we consider set of all invertible linear transformations and one member of it, and then we have any linear transformation from Rn to Rn such that this condition is satisfied. In that case, this B is also in omega. And in this condition, if you recall the proof, we had considered the reciprocal of this as alpha, and therefore this result could be rewritten, this hypothesis condition could be rewritten as norm of b minus a is less than alpha, because 1 upon this one is alpha. So if you see this, so means this condition, so we put alpha equal to 1 upon this one, so we can rewrite as norm of b minus a is less than 1 upon norm of A inverse, that means alpha. So this condition is useful for proving our second part also. And now let us see what second part comprises of. It again comprises of two subparts. First subpart is that we have to prove the set of all linear operators on Rn, that means the set omega, is an open subset of LRn. Now LRn is what? It's a metric space and a vector space also, and hence a non-linear space. So when we discuss about open set or open subset, so that means the universal space should be a metric space or a non-linear space. And here in particular, we have this as a non-linear space. So when we will be discussing about an open subset of this non-linear space, so the definition will be coming from open subset of this metric space, but metric written in terms of norm also, because we know that when a vector space is there and it is a metric space also, then we get a norm, or when a vector space has having norm, we can define a metric space also. So what we are going to use is, because we have already proved that the distance metric defined on this and norm defined on this, we have got both. So we can write the definition in terms of open for an open set in terms of distance also, that means in terms of metric also, and in terms of norm also, because this LRN is well known as a first as a vector space, and the norm is defined, and thus we get this as a matrix space. So better we will consider the open set definition for LRN in terms of norm, because for this the norm has been defined first. So we know that this is a set of all set of all linear operators, which is vector space, and norm is defined. Norm we know that norm of an element here, that means norm of a linear transformation from Rn to Rn is defined as supremum of all norm Ax, such that x are from closed unit sphere, and therefore we get the value as norm of A. Now in this we have to consider the open set, and then the second part means it's a mapping from omega to omega, so we will consider that mapping as a continuous mapping on this open set. And therefore we will when we will be learning the second part, so in that we will understand how the definition of continuity, which we have already discussed in terms of matrix spaces, can be rewritten in terms of a continuity of a mapping in terms of non-linear space. So now let us first understand what is the definition of an open set in terms of non-linear space, and then we'll be discussing that how omega can become an open subset of Rn as a non-linear space. So let us recall the definition from the matrix spaces, that if we are given X, a matrix space with respect to a metric D, and we have some subset E of this matrix space X, we say that this E is an open set if and only if it is neighborhood of each of its points. Now, what is the meaning of neighborhood of a point? So when we incorporate the definition in terms of symbols of this part, that it's a neighborhood of each of its points, then the definition of an open set becomes equivalently So E is an open set if and only if for each element, means each of x belonging to E. Now this part is that this E is neighborhood of x. So means for each x belonging for each point x belonging to E is neighborhood of x. So that is the definition. So if and only for each x belonging to x, what is the definition of neighborhood? There exists one delta radius such that the sphere with center this point x and radius delta is subset of this set E. So that is the part of definition, that E is neighborhood of x. So that is how this definition becomes. Now, what is the sphere in terms of when we write in terms of metric space? What is the sphere? It is with center x and radius delta. It is set of all those points y whose distance. So suppose y is here. Distance of y from the center x is less than delta. That comprises of open sphere with center x and radius delta. So sometimes in terms of metric space, I'll just give one example, that when if it is R3, so it's actually sphere what we discuss about, open sphere, that means without boundary. So without boundary points included into that, and all inside points. And if it is R2 or C, so it is called, in that case it is called open disk. So it will be just as it is looking like. So if we consider this full screen as R2, means part of R2, so this is what this is, open circular disk. So in that case we say it as open disk also. In R3 or in general, this open sphere is sometimes called open ball also by some authors. So this open sphere, which I'll say open sphere only. So that is its definition, that distance of y with from x, if it is less than delta, then that y is in this set. So that comprises of. So now we have this definition that for each x belonging to E, there exists delta greater than 0, which is giving a sphere, open sphere with center x and radius delta, which is subset of E. Now, when we say a set is subset of another set, what is that definition comprising of? That interpretation is that every element of the subset is element of superset. So let us re-express the definition so that we get this definition of open set in terms of distance. So what we will say, y belongs to this means this implies y belongs to E. So what this definition will become, a set E is open set if and only if for each x belonging to E, just like this, there exists delta greater than 0 such that y belonging to this implies y belongs to E. So y belongs to this set means distance of y from x is less than delta implies y belongs to E. Or we can write that for each x belonging to E, there is delta greater than 0 such that y belongs to E for all y such that the y belong to this set. That means distance of y from x is less than delta. So that is how the definition we are going to use for an open set for matrix space. And now let us connect this to the definition in terms of non-linear space. Now, because we will consider the non-linear space in our proof, so let us rewrite everything in terms of a non-linear space. Now, let us assume that this X, which we were considering as a matrix space, it is a non-linear space also. So in that means it's a vector space also. So in that case, how we will be able to rewrite this definition which we have got for open set? We will write that E is an open set if and only for each X belonging to E, exactly same. There exists delta greater than 0 such that y belongs to E for all y with, now this becomes what, for all y with norm of y minus x, that means distance between y and x becomes what, norm of y minus x is less than delta. So that is what we are going to prove for proving a set E to be an open set of a matrix, a non-linear space X. So in our discussion, what is our non-linear space? Our non-linear space is LRN. And what is open set we have to prove? We have to prove omega as an open set. So let us quickly see how this definition we are going to apply there. We'll say E is an open subset of the non-linear space LRN. So what we have to prove equivalently?
for each x belonging to E. So in that case, what we will write, for each A belonging to omega. So what we will do, we will fix arbitrary A belonging to omega, and then what we will show, will show that there exists some radius delta or alpha or whatever, such that whenever this is satisfied, means whenever some b minus a is less than delta, because a is here fixed, so b minus a is less than delta, then b should belong to E. So b should belong to omega, means our E is now omega in our definition. So let us recollect. You try to write it. We have to prove omega as an open subset of LRN. So what we will do, we will arbitrarily fix some a belonging to omega. So you keep writing on that. So you can pause the video and see that what we are doing, what we have to show. Let a belong to omega, and then what we will show, will show that there exists some delta greater than 0 or whatever distance greater than 0, such that when b minus a is less than delta, then b belongs to omega. So that is what we are going to prove it. And in that, if you would have already recollected the part A of our theorem, which I just reviewed there as a proof, if we are able to satisfy that condition, we are able to get that this condition here, because what we had there, b minus a norm is less than 1 upon norm of a inverse. That means that alpha. So we can get like this condition, and we have to see that how we get this b belongs to a through that lemma only. So let us go into that result. So that is what we have to prove. Omega is a open subset of norm linear space LRN. So from exactly from the part A, what we are going to get, that because we have considered A belonging to omega, so already A inverse exists, because it is set of all invertible linear transformations, and therefore A inverse exists and belongs to omega again, and therefore norm of A inverse is a finite real number and a non-zero, because this A and A inverse are invertible and hence cannot be zero linear transformation. So what we get is this is a non-zero number. So 1 upon that inverse of 1 upon norm of A inverse is alpha. So from exactly from that condition, if you rewrite, you should rewrite if this question comes, part B comes separately. So you should rewrite that portion as it is. And therefore what we get from that portion is uh, for every b which satisfies the for every b linear transformation belonging to universal set, such that if this condition is satisfied, then what happens, that b belongs to omega. That means if norm of b minus a is less than alpha, then b belongs to omega. So equivalently, just try to identify if the distance of b from alpha a is less than this real number alpha, then b belongs to omega. That means equivalently, I'm simply going back for your understanding. Otherwise, the theorem was proved here itself with just one line. So I'm just making 2-3 lines for your understanding only and going back. So what we have proved, that through this implicative statement, that with this radius alpha and center A, set of all points which satisfy this condition, they belong to omega. That means sphere with center A and radius alpha is subset of omega. That is what we had to prove, that for every a belonging to omega, this is the open sphere is inside. That means it's a neighborhood of every element of this one, and hence omega is an open set. So that proves our first subpart of part B, and now we will go to the second subpart of part B. For that, what we have to show, we have to show that the mapping from A to A inverse in omega is a continuous mapping. So now let us first of all learn that what is continuity. So just recall it, that continuity in a metric space is defined how. So 2-3 points we have to review here, and then we will be able to prove that. What was it? It was first result is that if we have a matrix space X with matrix D, then a non-empty subset of this matrix space is there. If we have, then that subset, if we get define a mapping, define a metric on this as a restriction of the original metric, means whatever the points we are considering in A, their distance in A itself is same as what was the distance of these 2 points in X, because A is what? A is a subset of X. So this is restriction metric we defined. So that is what we have to know. Why we are considering this? Because here what we are going to do, we are having omega as the open subset of LRN. LRN is actually a nonlinear space and matrix space. So we have to define continuous mapping. So first of all, it should be a matrix space, means to be defined. So that is why we are reviewing that restriction also subset, a non-empty subset of a matrix space with the restriction metric also is a matrix space. Then now if we have a mapping, a function from a matrix space X with metric D and to another matrix space Y, say Y, with maybe another metric D2. So we say that this function or this mapping F is continuous if and only for each element of the domain there exists epsilon greater than 0, such that the distance between x and a is less than delta, implies distance between fx and fa is less than epsilon. I have simply quoted here the definition from metric spaces. If you face any difficulty to remember this definition from metric spaces, and if you remember the definition of the continuity of real functions, in that case, if you remember, what is it? A mapping is a continuous mapping from R to R if and only for each a belonging to R there exists delta greater than 0, such that mod a minus a is less than delta. So what is mod a minus what is mod x minus a? It is distance of x and a. And then we say what this implies, mod of fx minus fa is less than epsilon. What I'm saying, if you write it, you will be able to remember and coordinate. So what is mod of fx minus fa less than epsilon? In terms of matrix space, this generalizes to distance of fx and fa less than epsilon. So that is how this definition of continuous mapping in a matrix space comes. And now we have already learned about norm-linear spaces. So we have to connect the definition of continuity in terms of norm-linear spaces also. So just before going into it, let us observe here. I have simply put dd here. So these are x and y in x. So in particularly to be specific, we should write d1 here, and because fx and fa are points in y where the d2 metric is being applied, so here specifically it should be d2. Maximum books actually ignore d1 d2, they start writing x to y and then they put d and d here also, and they say that where D has its own meaning in their own matrix spaces. That means if it is D1, if their points here are these, so D is D1, and if the points are here from Y, so D is from D2. So that is how books make it generalized. I just wanted to make you a specific understanding so that you, whenever you discuss this in terms of examples, you should be aware that this is a metric in domain metric space and this is a metric in codomain metric space. So that is how when we deal with examples, this discussion helps us there. Okay, now let us go to the norm-linear spaces. So exactly in terms of instead of matrix spaces, we will have norm-linear spaces. So I'm particularly considering here x with the norm 1 and y with norm 2, and we have to say that this mapping f is continuous. Now, what will be the definition? If and only if simply this part will be replaced with the norm of x minus a, norm 1 of x minus a, and this part will be replaced with norm of fx minus fa, norm 2 of fx minus fa. So exactly replacing this, we get the definition of continuity in a non-linear space. And one more trick which we are going to use in this proof, let us consider here. It is exactly for invertible linear operators on Rn, that means omega. So if we have two invertible linear operators A and B, so what we will have, A inverse and B inverse also belong to this one, and this is a trick which will be applied backwards in the proof. So I'm discussing here itself so that it is smooth. It becomes a smooth process to understand the proof there. If we multiply B inverse from left side and A inverse from right side to the difference of mapping A minus B, this linear transformation, then what we get if we apply the distributive law of multiplication over subtraction in the vector space LRN. So what we get is if we multiply both sides this way and this way, we'll get B inverse minus A inverse. The reason is given here, so it's too easy to discuss here. You'll be easily able to understand. So these are all the things which we are going to use. Let us go to the actual part of the proof. So what we have to prove? We have to prove that if we define mapping, I'm symbolizing here as psi, if we have a mapping psi from omega to omega defined as psi takes A to A inverse. That is how general standard books write it, means some stalwart authors write like this, and for our understanding we will write. So it's a mapping from A giving A inverse. So it's a mapping we are writing in a formal way that psi from omega to omega, which takes psi takes A to A inverse. So this is a mapping. We have to show that psi mapping is a continuous on this omega. So if we have to show on this omega, that means it's an open subset of LRN as a non-linear space. That is, we have already proved in our previous part, and therefore that qualifies to consider this mapping from omega to omega for continuity, because already we have proved that this is an open set, so that the part of continuity is discussable there. Just after ending the proof of this, I'll tell that why for discussing continuity we needed this set to be open. In fact, that is a part of general discussion which comes under the portion of continuity to be discussed on open sets. But okay, I'll discuss here itself, but let me complete the proof first. So what we have to show that this psi mapping is a continuous mapping on omega. So as we have reviewed that what we have to prove, we will consider arbitrary point of omega. Let us write A, and what we will show, we will show that for each epsilon greater than 0, I have written the mapping in this definition in terms of norm. So let epsilon greater than 0 be given to show there exists delta greater than 0 such that b minus a less than delta implies norm of psi b minus psi a is less than epsilon. So whatever was the role played by x minus a less than delta, and norm of fx minus fa is less than epsilon. So f mapping is replaced by psi here, and x and a are replaced by b and a, because b is the mapping general mapping playing role here, and a is the fixed mapping here. A is a fixed element of omega in terms of the non-linear space. Now, just one thing, it simplifies to understand what we are going to prove. What is the mapping psi A? Psi A gives A inverse. So just let us rewrite what we have to show. The conclusion part of this implicative statement, let us rewrite psi B means B inverse. Psi A means A inverse. So that is what we have to prove, that if norm of B minus A is less than some number, if we are able to get that number, then corresponding to any epsilon greater than 0, we should be able to get that norm of B inverse minus A inverse is less than epsilon. So as we have already seen that whenever we discuss implicative kind of statements like this, for each epsilon we have to get there exists delta, and we have to prove this condition. So how we start? We start always with the conclusion part, which we have to prove less than epsilon. So like that, let us consider the left hand side of this conclusion part. It is norm B inverse minus A inverse, and let us see how we can rewrite in terms of norm B minus A, as we have seen that proof goes on for proving like these things. So norm of B inverse minus A inverse, that is exactly what the trick comes here, which we had seen the last third review. So it is what inside the norm, it is nothing but B inverse A minus B A inverse. If you simplify this, you will get back this one, and we have got this, and now we are going to apply last part of our 9.7 theorem, C part. It was what? It was for 2 only. So there it was norm of means it's not N2, actually it's composition. So because we say this as composition when we discuss about algebra, so that is why I say it as N2, but otherwise it is composition. And there also this result was for composition, that we had composed B and A, we had taken norm of that, norm BA, it was less than equal to norm B into norm A. So let us apply that result, extend it to three compositions. So it is composition of B inverse. It's composition of A inverse composed with A minus B composed with B inverse. So what this result will be, that norm of this is less than equal to the individual norms multiplied here. This is actually multiplication of non-negative real numbers, because this is norm of this one, this is the norm of this one, real numbers. And now we know that norm of A minus B and norm of B minus A are same, because minus 1 will come out and we will take mod of it and it will be 1 only. So that is how we get it. And what we have got, let us separate it. So they are real numbers only, so we can apply the commutativity property and take it here. So it is norm of B minus A into, what is it? These are two real numbers, norm of B inverse and norm of A inverse. What type of real numbers in particular? They are actually non-zero real numbers, because A inverse and B inverse are invertible linear transformation. They have come from A. Both A and B are invertible, and therefore A inverse and B inverse are also invertible. And therefore A inverse and B inverse are also non-zero mappings. Therefore these norms are non-zero. You can refer to my previous videos where I have already discussed this, that how these will be non-zero numbers if linear transformation is an invertible linear transformation. So norm of an invertible linear transformation can never be zero. So with that, we know that we can divide it, and we will need to divide it. Why? I'll just tell you. We have to prove what? That this portion here is less than epsilon. For what? If we should be able to get some real number delta, such that norm of B minus A is less than that number. So we have got this something is less than equal to something into B minus A. See here, left hand side is here, it is less than equal to norm of B minus A, which is here, into something. So exactly what we have already done in our previous videos, what we will do to show is that this is less than epsilon. When this will be less than epsilon, if the bigger side becomes less than epsilon, this will also be less than epsilon. So that is what we will write, that norm of B minus A will be less than epsilon if the bigger side is less than epsilon. If means hypothesis part it will come into. So if this part into this part is less than epsilon. So because these are non-zero positive real numbers, so we can take it here, means technically what we do, we divide both sides by this bracket, non-zero number, non-zero positive real number, and therefore the inequality remains the same side and we can divide it meaningfully. This inequality becomes what? If norm of B minus A is less than this number. That is what we have got it. So this is less than epsilon if this is less than delta. Let us write it as delta. And that proves our that if for each epsilon greater than 0, there exists this delta greater than 0, such that delta this portion less than delta implies this is less than epsilon. So that is what I have already discussed, that how they are going to be non-zero and therefore we can divide it, and that proves our result, that therefore we have got this, and therefore this mapping psi from omega to omega is a continuous mapping. And now I just told that I will discuss that why we need a mapping omega to be means open set when we discuss about its continuity. So I'll just take you to the diagram previously made there. So why we need to discuss about an open set for discussing continuity. So this is a diagram, means when we discuss about open set. So here what we had assumed, that means in the definition of open set, that this x was fixed and we were taking any y here, such that this there exists open sphere which is contained in this set E, then only it will be open set. Actually, when we discuss about continuity, so what we do is this: we discuss that d of y minus x is less than delta implies d of fy minus fx is less than epsilon. So when we discuss about d of y minus x is less than delta, we say y belongs to E. So means that is what we have to consider. We say that y belongs to omega, the set which we are considering there. So how we can be sure that this element will always belong to that set, and this will be meaningful, and the other condition means in the continuity definition, I'll just take you there. Definition of continuity. So when we are writing here, That's the definition because X is a universal set. It is no doubt X will belong to X only, capital X only. But suppose we are discussing continuity here. So if we are discussing continuity of omega here, so what is the surety or E here? What is the surety that X will belong to E only? A belongs to E. So let us write F from E to E d1 to Y d2. When we will be able to say that this is continuous mapping, if for each a belonging to E, if we are saying E is continuous, for each epsilon greater than 0 there exists means delta such that we should write there exists delta greater than 0 such that distance of x minus a is less than delta implies this. Now fx is defined where? If x belongs to E here, if we are discussing on E. E is a subset of x. So when this will be defined, this will be defined if x belongs to E. How can we be sure that always x belongs to E? If we assume that E is an open set, then always there exists a delta such that dxa is will be contained in means will be less than and x will be in that open set E. So that is how this condition to be satisfied. Before that, we will be able to see that fx is defined there. So that was the conclusion of this lecture. So let us conclude with the proof which we have completed. That the second part, that omega from to omega, that mapping which takes A to A inverse is a continuous mapping. Okay, thank you.